Okay, so this is that follow-up video for Check Your Understanding number 5. Okay, so three things to, not three things, but I guess more two things to cover here. So the discrepancy that we had in number 5, remember, here to pull it up real quick. Remember the discrepancy is that after solving for everything, I ended up getting 280,999 watts, whereas in the key was saying, actually, bruh, it's 201,045.47 watts. And then that's before moving it into kilowatts, obviously. But anyway, so there was a large discrepancy here, and I was like, that seems a bit too big. Why are we seeing that? So here's why, in a way that from now on we can solve for work, and something I just completely forgot to even consider while we were working on this, while I was working on this in the video. So remember, potential energy and also kinetic energy, specifically the changes in them, are going to be equal to work. Okay, so think of it in this way. Let's say that in this scenario, this Bugatti, or not Bugatti, but this Lamborghini has kinetic energy. It'll have initial kinetic energy, and it will have final kinetic energy. Let's just say something like that. Okay, and we use both of those to find the change in kinetic energy. So in order to do that, it would basically just be the final minus the initial. Okay, this is then going to give us our work. So our initial, and this will give us our work done. So, and this is probably more closely how we ended up with the key saying 201,045.47 watts. Is because we did this. So here, I'll walk you through what this would look like. So, okay, so what would the initial, well, let's just do this real quick. Remember, kinetic energy is going to be equal to 1/2 times the mass times velocity squared, okay? And we'll use that for both of these here. So the change in kinetic energy is going to be equal to our final kinetic energy here, which is in here. I'm actually going to write this down here so I have more room. And our final is going to use our final velocity, and our initial is going to use our initial velocity. Okay, so that's 2.8, not 2.8 seconds, it's, what is our 26.8 meters per second. Okay, and we're just going to make it look like this. And then our mass, is, I don't know, I keep interrupting here, but our mass is going to be the 1,560, I calculated 66. Google, I think, will give you 1,564 kilograms. Here, it doesn't matter a whole lot. Maybe it does. It's something I haven't looked into. Maybe it does. But as far as I can tell, I don't think it really would matter all that much. But anyway, let's just do this. So it'll be the final. So it will be the mass times, remember, we're going to be using this equation for both sides. So it'll be the 1/2 times mass, which mass here is 1,566, times velocity squared, which is 26.8 squared. Okay. The minus, now what you'll notice though is that because we're starting from rest here, it's starting at 0 meters per second, we don't have any kinetic energy, so it'll be -0. So the change in kinetic energy here, or what our work is going to be putting this together, which when we put that together, the 0.5 times 1566 times 26.8 squared is going to give us this big old number, 562,381.92. Now, and that's joules. Now here, I'll pull out what I solved for with all of my long form stuff. So here's what we would find. This is what we'll find here for the work done on this guy. Here's what I solved for. So we're actually not too far off from the answer. And here, let me just pop something in real quick, just out of, because now I just noticed something. Oh, well, that's aggravating. Huh. Wow. So in the process of doing all this, I just realized that I don't know how I got this. I should never have gotten this. I must have forgotten the 0.8. Maybe I forgot the 0.8 when I was putting it in. I just did I'd probably put this in divided by 2. What I should have gotten was this. That's what I should have gotten, which is way closer. But anyway, so looking at this guy here, so 562,381.92 joules, which I brought this over to show you. This is what I originally found in the video. This is what we found when we found displacement, when we found acceleration, when we found force. This is what we got here, which is not too far off from this guy. And pretty much the only difference is, the reason why these two are not exactly the same is because here I didn't keep sig fig. So if I would have kept sig figs over here, we'd be way closer to this number right here. But honestly, it's pretty much just a difference of it looks like it's a difference of less than 1,000, which is pretty good. So anyway, here's still using the kinetic energy equation here in order to find our work done. So we've got our work done, and then it's just going to be P is equal to work over T, okay, which is going to be the 562,381.92 divided by 2.8, which is then going to give us a 562,381.92 divided by 2.8, which is going to give us 200,850.7 watts. So is it 201,045? No, it's not. Arguably, probably because that number again is going to take. Well, here, let's just see how we find that. So it'd just be 201,045.47 times 2.8. So that means that the key, found when I made the key, we found that it was actually 562,927. So we're off by just about 500 joules or so worth of energy, which again probably is just due to sig figs that we're not keeping throughout this. So this is what's so cool. So here's what I was able to find out using finding force, finding displacement, using initial and final velocity, and then putting it all together. Here is what I found, here's what I found for power. Here's what I found for power using kinetic energy. Like it's actually not too bad. Like for how off those two are, it's really not that bad. Because if we were to keep sig figs, if this was going to be put into sig figs, this would be 201 or 2.01 times 10 to the 6th power. And so would my other answer. My other answer would be the same thing. So we're very, 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 very close, which is pretty cool. So anyway, that's all I wanted to show you. And I'm glad I caught whatever mistake I just caught while making the video. So hopefully you were able to catch this before me. But I have to apologize just for forgetting this part of finding the work done. It's just work is just finding the change in energy. And that just means what's your final energy minus your initial energy to find out your work done here, and that's what we did here. So anyway, yeah, because you can't really do much more when your original starting amount of energy is 0, and then this is what you end up with. Okay. So anyway, okay guys, that's it for the video. If you still have questions, make sure you get a hold of me. If not, I will catch at you later.